Let's see here. So we were talking about equilibrium constant. We also saw Q, which is the reaction quotient. So remember that Q is really calculated the same way as we calculate the equilibrium constant. We do take the products over the reactants. We also still use the coefficients as the exponents when we do so. And really, there's kind of two reasons why we use Q and a couple of places where we would use Q. As we talked about, we can compare Q to the K value, and that will tell us whether or not we're at equilibrium. So that's the main type of Q question, which is, is this system pretty much at equilibrium? And the second thing that will sort of tell you is if it is not at equilibrium, really which way the reaction needs to proceed to reach equilibrium. Does it need to make more products? Does it need to make more reactants? And when we compare the Q to the K value, and if Q is greater than the K value, it first tells you it's not at equilibrium. And to make more reactants would be necessary to reach equilibrium. If Q is equal to K, then that system is at equilibrium at that point. And obviously, it doesn't need to go anyway. It was perfectly fine the way it is. And if Q is less than the K value, it again tells you it's not at equilibrium, and it needs to go kind of opposite of where that little guy is pointing, and it needs to go towards the product side to make or reach equilibrium. So we do use Q in just a straight sort of question like that. Is the system at equilibrium or not? And really, it's a situation where maybe we're given initial concentrations, or we're not really sure if these are equilibrium concentrations that are given to us. We could calculate the Q. Obviously, we would need the K value given to us. Obviously, as well, the only way to calculate Q would be you would need to be given the concentrations of everybody so that you could plug it in. So that would obviously limit your ability to calculate Q if you are not given, obviously, the initial concentration sort of everybody. The second place where we could kind of see Q come into play is when we really do equilibrium type of calculations and do equilibrium problems. And those are, we also finished up talking about last time, which is where we use these ICE tables to do so. And we use ICE tables where the I is the initial, the C is the change, and the E is the equilibrium coming through. And we use this to figure out really the equilibrium concentrations of all species. And we could also, as we talked about, do this with pressures as well. So we could kind of use this ICE table approach for both things that are concentrations and things that are pressures as well. Remember that if you go into an ICE table, it definitely needs to be in atmospheres when you're doing the calculation. Even again, if it gives it to you at some other pressure unit and it asks you to give it in some other pressure unit to do the calculation part, it has to be in atmospheres, and then you have to kind of do the conversions at the end. So if we do have an equation like our 2A plus our 3B goes to C, we would write our equilibrium expression of our products over our reactants. There we go. And that would equal some type of number, or whatever it may be. Good, we're good. Did everybody get the roll sheet? Yeah, perfect. That's good. And what we do is if we put our initial concentrations in here. And as we saw on the example we were doing at the end there, if you're really not given anything in terms of the products, it's pretty safe to assume that's going to be zero. So again, if you don't see any products sort of given to you in terms of concentrations or pressures, you can just use zero for that. The change part's really the important part, kind of the ICE table. It really is sort of what we're looking for in terms of trying to solve for the X, which is what we use to represent the change. In this case, if we had no products, we would assume that the reaction is going to head towards the product side. And that would mean that we would expect the reactants to be decreasing with time, and we would expect the products to be increasing with time. So we represent that by minuses and pluses. In this case, this would be minus 2x. This would be minus 3x. And we do have to take the coefficients into account when we do the change line, and that would be plus x. If we do not take the coefficients into account, we will not have the right mole-to-mole relationship, stoichiometry, and your calculation will be incorrect. So that's a really important part of the change part, is to make sure that you do take those coefficients into account. At that point, we just carry it down here. And we take whatever we get here in the equilibrium line, and we basically put it into our equilibrium expression, and we basically will solve for x mathematically, however you need to do that. Again, probably the most complicated way that we'll do it, as we talked about, is like the quadratic, which is, again, minus b plus or minus the square root of b squared minus 4ac divided by 2a. And again, that is when you get your equation basically into the form of ax squared plus bx plus c is equal to 0. As we talked about, if you do use quadratic formula, you will get two answers, and one of the answers will not make sense. And what we typically do when we do solve for x is, when we get that x value, that is all the x values in basically our table. And that will allow us to get to the equal concentrations of everybody. And again, obviously, if we're dealing with pressures, the equilibrium pressures of everybody, and it works basically the same way. Any questions on any of that stuff there that we did last time or talked about? Okay, so yeah. Yeah. Where you have the a and the b and the quadratic, they actually come from this equation. So when you would put this into here, you basically would try to solve it so that you'll get something that looks like this. And then really it's the coefficients in front of the x squared, the x and that go into there. And by the way, you do keep it if it's negative, you throw negative into those numbers as well when you go into that equation. So, you know, if you have like a minus something in that sort of formula, you would put it into that equation the same way. Other questions? All right, so we were playing with one that was kind of made up numbers. So let's take a look at a real sort of example here, and we'll go through it together to see how all these sort of parts come together. Hopefully good, I hope. All right, so we have this reaction here, which Br2 is going to Br minus. The equilibrium constant is 7. And if we started with an initial concentration of Br2, we want to know what is everybody's equilibrium concentration. So one of the first things you could do, if you like, is you could write the equilibrium expression for this, which would be K is equal to the concentration of Br squared divided by Br2 here. And that would obviously equal 7. At this point, we can do our ice table, which, as I think mentioned last time, pretty much in this class, you know, almost can't go wrong trying at least an ice table on a lot of things that we do. We're going to initially put in our concentration of our Br2, which was the only thing given to us at 0.663. And again, since nothing was given to us in terms of Br, we can safely, hopefully, assume that it is 0. This also helps us understand probably the direction of this equation. We can make a pretty safe assumption that this equation is going to be going towards the product side, as we have no products to start with. So the forward direction of this reaction should really predominate here as we go through it. So that's going to help us with our change part. We know that this then should be minus x. Again, the coefficient here is 1. And on this side, we should be gaining it, which would be plus 2x. I forgot to mention a second ago, but this again would be the other place where if we were able to calculate Q, that's what it could affect here in our ice table, right, is the change part, which way the direction of the reaction is going. In this particular problem, we cannot calculate Q, right, because we don't have enough information to do so. So you don't have to worry about it in this case. At this point, we're going to just kind of carry this down here, and we're going to end up with 0.663 minus x and 2x. Any questions on the ice table here? At this point, the goal is really to solve for what x is equal to. So we will take our equilibrium sort of values here, or things that we got, and we're going to put it into our equilibrium expression. So that will give us something like K is equal to 2x, and we're going to square it. divided by 0.663 minus x. And once again, that's all going to equal 7 at this point. We got to do a little cleaning up here. So I'm going to do the top part. And as I mentioned, we want to square not only the x, but also the 2, which is a super common mistake that people make. They just leave it as 2. We are also going to multiply what's on the bottom here to the other side. So I'm going to do that and bring that over to the other side. And if I do that, that will give me, looks like 0.663 times 7. Gets me a 4.641 minus a 7x. So this is going to get us into our quadratic sort of equation here. We want to set it equal to 0. So we basically want to bring everybody to the same side of the equal sign. And truthfully, it doesn't really matter which way you go, but most people will try to keep the x squared positive, but you don't have to, but most people will try to keep the x squared positive. That means we're essentially going to take everything on this side and bring it back over this way. And when we do so, we will end up with 4x squared plus 7x minus 4.641 is equal to 0. I basically subtracted this guy, added that guy to the other side. Yeah. Any questions on that there? That is going to give us our A, B, and C that we need for the quadratic here. That's going to be an A. That would be our B. And that would be our C. So going into it, we get x is equal to minus b plus or minus the square root of b squared minus 4ac, I hope so, divided by 2a. So we will end up with here basically that x is equal to minus 7 plus or minus. Now, if you put all that into the square root part, you will get basically 7 squared minus 4 times a, which is 4, times c, which is negative 4 point, oh, it helps hit the right number, 4.641. And inside the square root, before you take the square root, you should get something like 123.256. And then if you take the square root, you'll end up with something like 11 point, we'll call it 10 at that point. That's all going to be divided by 2 times a, which is 8. I'll try it without my calculator in this case. Any questions on that? So again, just putting those letters into there and solving for it. As we talked about last time, we're going to get 2 values here. So I'm going to do the plus first, and then we'll do the minus. So in this case, I'm going to take basically minus 7 plus the 11.10 divided by 8. That gives me an x value for the plus way of 0.513. I'm now going to do the minus, so negative 7 minus the 11.10. There, 2 O's. And divide it by 8. And that's going to give me a negative 2.26. Any questions on how to solve that there? So at this point, these are our 2 possible x values, and we could probably clearly see that one of them is probably not a great one, and that would be our negative, because those x values are going to go back into here in the equilibrium line, and clearly if I put that negative one in there, that's going to give me a negative concentration, which we cannot have. So that means by default, this is going to be our winner there. So we're going to basically use that and put it back into each of them. So for our concentration of Br2 at equilibrium, that would be 0.663 minus our x value of 0.513. And that's going to give us 0.663 minus 0.513. I'll give us something like 0.150, and this would be molar since it is a concentration. And we'll do the same thing here for our Br at equilibrium would be 2 times x, which would be 2 times 0.513. And that's going to give us, and we'll call it 1.03 molar in this particular case. Now, if we, that would be obviously our equilibrium concentrations of each of these guys when this reaction reaches equilibrium. Any questions on any of those steps there? This is math. Yes, that's good. Good thing about math is I can know if I screwed up along the way, because there's going to be a lot of places where you could screw up for sure. Yes, and I could check myself how in this case. That would be a good way to do that. So now that we have the equilibrium concentrations, we could actually stick it into our equilibrium expression, and it should be in the ballpark of 7, which it is in this case. It won't be probably exact with rounding and stuff, but it should definitely be in the ballpark. So, you know, we could take these values now and put them back into here, and we should get somewhere in the ballpark there of 7. And it's a good idea to do that if you have time, because this one is not very complicated in terms of the quadratic. There are some that is very complicated in terms of the quadratic. There's a lot of numbers and zeros, and it's a very common mistake that people will kind of miss some zeros along the way and stuff like that. So a good thing to do is always maybe throw the answers back in and check it to make sure, again, you hopefully didn't make a mistake. Not guarantee that it will catch everything, but it should catch some really bad mistakes just in case. Yeah. Any questions on any part of that there? All right, so we also had for this one, by the way, is this a large value of K or small value of K? It is, so we should expect what at equilibrium? Mostly products, and that is sort of what we see, right, in terms of the concentration, so that worked out good too, in terms of that calculation. All right, so I did one, so I guess it's your turn to do one here while I take a nice nap and wake up at some point. All right, give this one a go here. You got 0.5 moles of H2, 0.5 moles of I2. It's in a 1 liter flask. What is everybody's equilibrium concentrations? K value here is 54.3. See what you come up with. All right, let's try that again. Okay, so here we're obviously dealing with equilibrium. So let us start with our equilibrium expression, which would be our HI. Once again, we do need to square it because of the coefficient that we see. That will be divided by our reactants, which would be H2 and our I2 in this case, and that's going to equal 54.3. We obviously need the concentrations here of everybody. They were given to us in moles and liters, so we can get the concentrations of our H2, which would be 0.5 moles divided by 1 liter, which means it's basically going to be the same number here. And the same thing here for our I2, which would be 0.5 moles divided by 1 liter. And obviously here we are not given anything in terms of our products, but we do have our initial concentrations here. So we could get right into the ICE table to solve this. So I'll just borrow here, maybe. There we go, that'll work. So our initial is 0.5, 0.5, and again, nothing given. So safe to assume that it's going to be 0 in this case. We then could go to the change part. Let's rewrite this real quick. Change part here, we could again assume that it is heading in this direction because we have no products to begin with. So there's going to be minus x, and a plus 2x. Once again, taking into account those coefficients there as well. That means when we get to equilibrium, 0.5 minus x, 0.5 minus x, and 2x in this case. Any questions on the ICE table or anything like that? So now again, the goal here is to solve for x. So we're going to take what we got here on the equilibrium line. We're going to put it into our expression and do a little math. So we will put it in. That will give me 2x, and it's going to be squared divided by 0.5 minus x times 0.5 minus x, all equaling 54.3. We want to mathematically solve this, right, without having a big headache. So hopefully you looked at this and saw you could do what? Yeah, it's a perfect square on both sides. So you could just put a big old square root on both sides. A lot easier math, I'm assuming, in that case, right? So do a little square root action on both sides would be really great. Just a friendly reminder, you don't have to use quadratic in every situation. So, don't make life hard on yourself. But if you love the quadratic, go for it because, you have fun with it. But it might be quicker in some cases. You don't necessarily have to do it. So we'll end up with 2x up on top. We'll end up with one of those guys on the bottom. And the thing that I personally usually forget to do is actually square root of 54. So let me actually do that before I forget. So we want to take the square root of 54.3. And that's going to give us, I'll call it 7.3689. Now we're going to multiply this to the other side, and that will give me 2x is equal to 0.5 times our answer there of 3.6844 minus 7.3689x. We're going to add this back to the other side. That will give us 9.3689x is equal to 3.6844. Lastly, we're going to divide that back to the other side, and we will end up with a 9.3689, and we get our x value of 0.393. Any questions on that? So clear here, we didn't use quadratic. We got one x value, so that hopefully should be the x value. So we're going to now put that x value as it represents every x that you see in this ICE table back into here. So that would give us the concentration of H2, which would also be the concentration of I2 in this case, since they're basically the same. 0.5 minus x. And that would get us here 0.5 minus 0.3. Try the right numbers there. 393 gets us a 0.107. We do need the molarity as they are concentrations, and our HI in this case would be our 2x, which would be 2 times 0.393, and that's going to get us 0.786 molar in this particular case. Any questions on any part of that calculation there? Once again, if you take those values and you put it back into the equilibrium expression, you again should be in the ballpark of 54, basically. Yeah. Any questions on any of that? So again, you don't always have to use a quadratic. Sometimes you do need to use a quadratic. There are some times where you don't. But even if you did the quadratic and did it correctly, you should end up with the same at the end, basically, answer. All right, that was a fun one. Let's do an even funner one. All right, here we go. Initial concentrations of H2, I2, HI, 0.00623, 0.00414, and 0.0224. The K value is 54.3, so we're using the same equation. Okay, let's see how we're doing on this one. This one's a little bit more involved than, say, the previous one, I think. So we are dealing with, obviously, still equilibrium. So we could start with our equilibrium expression, which, since it's the same reaction, will be the same expression as the last one, which is something that looks like this: our HI squared, our H2, and our I2. And once again, that is going to equal our 54.3. In this particular case, we're given the concentrations. We're actually given the concentrations of everybody, which means perhaps I should calculate Q. So this would be a place where you might want to calculate Q, since we are given the concentrations of everybody. We probably know, for example, that it's probably not at equilibrium, otherwise it's not much of a problem to do at this point, but it could help us reassure which way this reaction is heading, just to make sure we are doing the change part correctly, right? So if we're going to calculate Q, it is also calculated the exact same way as our K. And we will put our numbers in. And that would give us here our 0.0224 divided by our H2. Just that guy there, which is 0.00623 and 0.00414. That gives us 0.0224 divided by 0.00623 and 0.00414. That gives us not that number. Try that again. 0.0224 divided by 0.00623 and divided by 0.00414. Yes, and I forgot to square that number, so let me square that number and try it for a third time here. There we go. I'll keep going until I find a number I like. Let's see. There we go. There, that and that would be good. All right, how about 19.4? I'm gonna go with that. That looks good. So we have a 19.4, which is our Q value. In this case, our Q versus our K. Our Q in this case is actually going to be less than our K value, as our K value is 54. That means it's not at equilibrium, which is not much of a surprise here because not much of a problem again if it was. But it does confirm it needs to go which way to reach equilibrium. Yeah, it needs to go to the right there towards products. So now that when we do our ice table, we could be very confident that we are putting our minuses on the right correct side and our pluses on the other correct side. Any questions on that so far? All right. Don't forget to square it. All right, let's try that again here. So let's get into then the ice table. So I'm going to rewrite it here. So I got H2. I got a little I2 action. And a little 2H on. Yeah. When Q is less than K, it has to go towards products to make more. So the way I remember it is, and you could do it either way, but if you put all the Q's on the left and the K's on the right, it's basically opposite of where this guy is pointing. Or I guess if you flip it around, it's the same way it's pointing if you want to do it the opposite way and put the K's on the left. But that's what it means in that case, yeah. Other questions? Okay, so we'll put into here our initial, which is 0.00623, 0.00414. And again, here we do not have a 0 on this side. It is 0.0224. So again, that is why we were able to calculate Q, because we were given, again, the concentrations of everybody. Previous problem, we weren't, so we could not calculate it. Change is going to be minus x, and plus 2x, which we confirmed by doing our Q calculation that it is heading in this direction here to reach equilibrium. Coming down here, we're going to just carry everybody down. So 0.00623 minus x, 0.00414 minus x, 0.0224 plus 2x. Any questions on the ice table here? Just like normal, you got a lot more numbers here, but we're going to put it into our K expression. So basically our products over our reactants. So we're going to take our 0.0224 plus 2x, and we do need to square it because of the coefficient. We're going to divide it by 0.00623 minus x times 0.00414 minus x. And that's going to equal 54.3 in this case. This unfortunately is not a perfect square. So you got to do a little factoring in and out, all that kind of stuff that we were talking about the other day. Or you could just go to the next problem. Might be easier. I don't know, but we'll see. All right. So we're going to do some factoring out of everything. So I will start with, I'm just going to kind of do them separate from each other and then kind of put everybody back together. So I'm going to take the top part here on the left, and that's basically 0.0224 plus 2x times 0.0224 plus 2x. And again, if you do a bunch of the factoring and all that good stuff, you end up with, I hope, 0.000500176 plus 0.0448x plus 0.0448x plus 4x squared. Comboing everybody together, you end up with 4x squared plus 0.08. I said it, but I did not write it. Let me try that again. All right, 4x squared plus 0.0896x plus 0.000500176. So that's basically the top part solved out. We're going to do the same thing for the bottom part. Do it maybe in a different color here. So we'll do the bottom down here. So we're going to take for our bottom here our 0.00623 minus x, 0.00414 minus x. And I'm assuming everybody knows, but just so we remind each other, right? Out and in, right? And then in and out. Yeah, just like so is what we're doing. And if you do that sort of move there, you will get 0.000025792 minus 0.00623x minus 0.00414x plus x squared. And again, kind of cleaning up everything on that gets us for the bottom, x squared minus 0.01037x plus, really could have used a little scientific notation, but well, I wrote the zeros, I'll go with it, 25792 in this case. Any questions on that? And obviously we did the in and out thing on the top one as well. Coming from here to here to here and here to here, right? All right, so now that we got the top and the bottom sort of factored out, I'm gonna throw those back together on the next page, and then we're gonna do the rest of the math here. Any questions on that so far? All right, so going to the next page here, just taking our top part and our bottom part and putting it back into our K expression. Up on top, we had 4x squared plus 0.0896x plus 0.000500176 over x squared minus 0.01037x plus 0.000025792, and that still equals 54.3 in this case. We're almost done with our math here. And we're going to then take everything on the bottom and multiply it over to the right-hand side. That means on the left-hand side, we didn't do anything, so it stays the same up there on top. So 4x squared plus 0.0896x plus 0.000500176 equals, when we multiply that to the other side, we're going to get 54.3x squared minus 0.563091x plus 0.001400506. Now we take a breather and we relax for a second. We think about our weekend plans. We try not to look at a paper that looks like this all week, right? All right. Just so to show you, I did it by hand myself as well with you. All right. So now we're going to bring everybody to one side to combine everybody up. Again, I'm going to keep probably the x squared positive. So for me, I'm going to take everybody that's on this side, and I'm basically going to bring it over to that side to bring it all together. And when you bring it all together, you get your final happy quadratic equation of 50.3x squared minus 0.652691x plus 0.000898746 equals 0. That finally is, if you're still with me and haven't walked out yet, that is still our A, B, and C value that we need here for our quadratic. Yeah. Any questions on that so far? All right, if you have any energy left, we'll put it into our quadratic at this point. So x is going to be equal to our minus b, which should then turn this into a positive number. That's going to be plus or minus the square root, again, of our b squared minus 4ac. And if you do that inner part there, you will get, trust my number I have written, so I'm going to do it one more time myself. It's about 0.652,691 squared minus 4 times A, which is 50.3, times our B, which is 0.000898746. It's going to give you, before you take the square root, inside 0.245177846. Do a little square root action here. I'm going to drop off some of these numbers here, and then we're going to end up with 0.49515. We'll call it. That's then all divided by 2 times A, which is 2 times 50.3, gives us 100.6 on the bottom. That then will get us to our 2x values here. So we get an x if we do the positive way of 0.652691 plus 0.49515 divided by 100.6. And that gives us an x value of 0.0114. And if we do the subtraction, 0.652691 minus 0.49515 divided by 100.6. Are 0.00157, we'll call it in that case there. Any questions on that? In this case, we actually did get 2 positive values for x, but again, one of them will not make sense. So help us to decide which one does not make sense. We will go back to our equilibrium line. So I'm just going to rewrite our equation in just the equilibrium line from our ICE table. And at equilibrium here, we had 0.00623 minus x, 0.00414 minus x. And for this guy, we had 0.0224 plus 2x. So just looking at it, this number here looks a little too big. Yeah, if we put that back in, we're going to get a negative number. So that means that this guy right here hopefully should be our correct x value. So again, although you do get 2 positive numbers here, when you go back and put it into that equilibrium line, it does yield you a negative. So that's going to be your bad number. I think we talked about last time, you do have sort of 3 possibilities when you solve these. You could get 2 positive numbers, 2 negative numbers, or a positive and a negative number. So what you want to determine is when you put it back into the equilibrium line, which one gives you a negative number, and that would obviously be your bad choice not to use. All right, so let's finish it up here. Our concentration of H2 at equilibrium would be 0.00623 minus our correct x value. They're at 0.00157, getting us 0.00623 minus 0.00157, 0.00466 molar. For our I2, it would be 0.00414 minus 0.00157. And that's going to get us 0.00414 minus 0.00157. 0.00257. Again, they do need the molarity on it as it is concentrations. And lastly, our HI. Remember that we did have an initial concentration, so we want to make sure that we do that. The other common error that sometimes people will make is they're so used to doing minuses at this point. They do a minus here, but it is a plus. Yeah, so that's plus 0.00157 as I run out of room there in the corner. So 0.0224 plus 2 times 0.00157 going to get us 0.0256 molar, we'll call it. And those would be our equilibrium concentrations here. Yes. Any questions on any of that? I'm scared to do it, but I will do it. 0.0256, and I will square it, putting it back into our expression and dividing it by 0.00466 and divided by 0.00257. Got a 54.7, which is pretty close to 54.3. Thank you. I'm here twice a week. 2 shows data. Yeah, I know. I told you at the beginning, it was just a small portion of this chapter we're going to do. It's only like 3 problems today. Any questions on this one? So this brings up a couple of very important things. First off, you do need to be able to do this, yes? Yes. Secondly, you want to be really careful, obviously, as you're moving around, that you don't lose zeros, you don't add when you should be subtracting. So although I kept a lot of zeros here, you might want to cut some of them off, maybe go scientific notation on some of it. You know, keep some of the significant figures, but try not to lose zeros along the way. And recopying, you know, sometimes it happens. Even I messed up there on the first part. I've kept forgetting to square it. So there's a lot of places where it can go wrong for you. So that's why at the end, it's a good idea to throw it back in there and make sure you are at least in the right ballpark. You won't maybe catch all the errors, but, you know, if you're close to where it should be in terms of the K value at the end, when you put it back in, you know, well, there's maybe a good shot you didn't mess up, right? Again, if you're very far away when you put it back in, you might have lost a 0 or something along the way in your calculation. Any questions on that one? Yes. Why did I choose the one that we use versus the one here? Yeah, so really, if we took the other number and, for example, if we put it into this here, which is the equilibrium line, it would give us a negative concentration when we put that X value in there because it's larger than what we're subtracting it from. So that we know for sure you can't have a negative concentration. So for example, if we did that, we took that one and we were going to use that first one, we'd go 0.00623 minus our 0.01, I think 114. And if we do that, that would tell us that at equilibrium, if that was our X value, we would end up with a X value of like -0, or a concentration of -0.00517 molar, which clearly you cannot have a negative concentration. So that is typically what will happen when you use the quadratic formula and get those 2 values. Is one of the values when you put it back into that equilibrium line will yield you a negative value, and that's usually the bad one. You should not use that one, and the other one should be the good one. And again, sometimes you may get 2 positive numbers, 2 negative numbers, or a positive negative number, but that's really what you should look at is when you put it back in, you know, do you get a negative value? And I say that because sometimes it is possible, and maybe not this chapter, later chapter, when we're doing some more ice tables, that you could get 2 negative values for the X. And sometimes people will go, oh, I must have screwed up. I got like 2 negative values or something when it came out. But it actually will be okay in some cases when you put it back into the equilibrium line. It will still give you a positive number, even though you got a negative value for X. So just make sure you throw it back in and check it that way. Well, now that you're warmed up, I promised him 3 questions today. So this is our 3rd one. There we go. And again, I'm going to take a power nap. I'll catch you in like 20 minutes. We'll see how we do. All right, give it a go here. Okay, let's take a look at this one here. So as I mentioned before, we do have a Kp value. We do have pressures given to us. And again, atmospheres is definitely the pressure unit that you want to make sure you're using, definitely in these ice tables. So as I mentioned a number of times, even if it's giving you some different unit and it wants the answer in a different unit, get it to atmospheres to go into the ice table. So we will do our ice table here, and if I will borrow there's good. So initially here we have a pressure for N2 of 0.0 0.862. We got a 0.373. Once again, we are not given anything in terms of our products, so it is safe to assume we are going in this direction. Again, there's no way to really calculate Q, so we can't have to worry about that. Change here will be minus x minus 3x, and this will be plus 2x. This is going to give us an equilibrium line of 0.862 minus x, 0.373 minus 3x, and 2x. We'll put this into our expression, which I didn't write on the last page, but we'll do it here. It is the partial pressure squared of NH3 divided by the partial pressure of N2 and the partial pressure cubed of H2 in this case, yeah. Now that equals something, 4.31 times 10 to the minus 4 in this case. Yeah? Any questions on the ice table or anything like that so far? We're then going to take our equilibrium line into here. That's going to give us a 2x squared divided by 0.862 minus x, 0.373 minus 3x, and we do need to cube it, and that equals 4.31 times 10 to the minus 4. At this point, we do need to solve it, and that means that we should leave this class right now immediately and never come back to any of this equilibrium stuff. Congratulations, it's over. The Chem 51, we're done. No. All right, so clearly we don't want to do quadratic because who remembers that math? I don't remember that math or how to do that. So we want to think maybe about a better way to solve this problem besides just going on to the next problem. But so when we look at this and we look at the equilibrium constant, is that equilibrium constant a large value or a small value? Small. It is a small value, right? So when we look at this equilibrium constant, that is a small value. And because it's a small value, that means that when we reach equilibrium, should we mainly have reactants or products? We should mainly have reactants, which are these guys. And that means that the change part, which is represented by X, should actually be relatively small. So it shouldn't be a lot of it going to the other side. So because the K value is small, we can assume that X is equal to 0 because it's going to be relatively small and negligible. We clearly cannot assume all X's are equal to 0 because we have nothing to solve for at that point. But it is all the X's that we would be subtracting from a number is the ones that we're going to assume is equal to 0. We don't assume this one's equal to 0 because it started at 0. So anything that you get above 0 is pretty significant, right? So that's why we don't assume, obviously, that one is 0. Otherwise, as well, we have nothing to solve for. So that's going to make our math here hopefully a little bit easier. We'll have 2x squared divided by 0.862 times 0.373 cubed is equal to 4.31 times 10 to the minus 4. That to me looks a lot easier to solve than the previous one, and I'm going to roll with this one. So I'm going to clean up the bottom and then multiply it to the other side. So I got 0.862 times 0.3 negative, no, point, still negative, try the negative there, 0.373 cubed. And that gives me something like 0.0447. We're going to multiply that to the other side, 4.31 to the negative 4, making sure we use our exponent button. That will give me on the left-hand side, 4x squared is equal to 0.00001928. We're going to divide by 4. And then also take the square root of it. So we're going to divide by 4 and then take the square root. Don't forget the square root part. And that gives us an X value of 0.00220 as our X value. First off, any questions on that math there? So again, I divided by 4 and then I square root it down. Yep. Now that we made this assumption, when we make an assumption like this, we actually have to check our assumption to make sure it's okay. And the way that we're going to do it is by what's referred to as the 5% rule, which means if you check your assumption and it's less than 5%, you're good. If it's 5% or more, then you need to go solve it another way, which is the quadratic, which then we cry at that point. So let's hope not. So that's going to be 0.00220. We check it by dividing it by what we were going to subtract it from. So 0.862 times 100%. That gives us 0.00220 divided by 0.862 times 100%. And that is about a 0.255%, which is less than 5. And now we smile again. Yes, because we are happy. You could actually check both of them. So to check this guy, you would take actually 3 times that X value divided by 0.373 and times it by 100. In most cases, if one checks out, they're probably all good. So you don't necessarily have to check them all, but usually if one's good, they all are good. So that is going to be our X value, which we're going to use to go back into our equilibrium line here. So to finish up this problem here, we're going to get the pressure there of N2, which would be 0.862 minus 0.00220. And that's going to get us 0.862 minus 0.00220, 0.860 atmospheres, as these are pressures. So atmospheres is the unit. The pressure of H2 will be 0.373 minus R3 times our X value. And that will give us P373 minus 3 times 0.00220. That's going to give us a 0.366. Once again, these are atmospheres. And lastly, for our NH3, I'll come over here. The pressure of our NH3 is equal to 2x, which would be 2 times 0.00220. And that will get us 0.00440 atmospheres in this case. Yeah. And again, we could check it by taking our product there and squaring it, dividing it by our H2 and cubing it, and dividing it by our no, I said the other day, National Pirates Day. Divided it by our 0.860. That gives me something like 4.6 times 10 to the minus 4. I hope that's pretty close to our X value there. There it is. Not too bad. Any questions on any of those? Yeah. So it does need to be the equilibrium constant does need to be considered a small value. So remember that a large value is pretty much anything 1 and above. So anything pretty much with a negative exponent there, you're good to go on it. You should check it. It will be good in some cases. It will not be good in other cases. So there will be problems where you'll make the assumption, but still has to go back and solve it using the quadratic formula. Yeah. Because basically what we're doing is that's the initial pressure, initial concentration, basically. So as long as the change is less than 5% of the initial concentration, then it's assumed to be negligible. It's not that big of a change. If it's anything bigger than that, then it's too big to call really the change 0 at that point. You'd have to solve with some other. You could have. So if that was your question, you could do either one. Usually if you check one and it's good, the other one's usually good. But if you were going to do the other one, you technically should also multiply the X value by 3 first and then divide it and then times it by 100. A couple of things before we all run out. We've now seen through our ICE table expertise here, 3 different ways to solve it, right? We could use quadratic, we can make an assumption if it's appropriate, or we could have a perfect square. And these will be the 3 ways that you'll be able to solve these type of problems. There is another way, which is known as successive approximation, where you just kind of guess a number. Now, So for example, on this one, we know that X is, for example, has to be less than like 0.373. So you would guess a value less than that and put it in. You would put it into every place but the X on top. And then you would solve for the X on top. And you would go until the number you put in and the number you get out is the same. Which if you're really crappy at that, it will be a long day for you. Yeah. So we will not solve any problems through successive approximation, but you might see it in the book or, sometimes a solutions manual, they'll solve it that way. We won't do that. So quadratic, again, is the craziest that we'll get.